Hi, my name is Shahnawaz. In last lecture, the examples of categories that we mentioned are important, but they could give a false impression. In each of these examples, the objectives of the categories are sets equipped with some structure, and the maps are the functions that preserve these structures. However, all categories are not like that. In general, the objectives of a category are not sets equipped with some extra stuff, and the maps need not be functions in usual sense. So we can make a remark here. So we have a remark, and it says that the objectives of a category need not be remotely like sets. And the maps in category and the maps in a category need not be remotely like functions. Now we do some examples that illustrate these pointers. So we are now going to discuss categories as mathematical structures. So a category, we know a category can be specified by saying directly what its objectives, maps, composition, and identities are. So we have the first example. So these are the categories as mathematical structures. So the first example is, so there is a category, the empty category with no objects or maps at all. So we denote this category by, so there is a category denoted by the empty set. So this category has no objects and no maps. Also there is a category 1. So also there is a category denoted by this bold one uh, with exactly one object and only one map, that is the identity map with only one object and only the only the identity map on the object. So we can draw this category. So it can be drawn like this. So we just have one object and one map. So we can draw this category like this, or just a dot. since every object is required to have the identity map on it. So we usually do not bother to draw this arrow because it is understood. It's by definition there. So there is a category that can be drawn like this. So there is a category that can be drawn as, so let us suppose this category has two objects and one non-identity map. So as we mentioned here, we do not bother to draw these arrows. I mean the arrows on the objects because by definition these maps are there. Or we can call this object A and other B and we have this map here. So this category has, this has two objects and one non-identity map. From one object to other, from one object to other. Similarly, we can draw more. mm, I mean, we can draw some more categories which are somewhat complicated. So we can draw more complicated categories. So, for instance, that is, for instance, we have the following categories. Let us suppose we have two objects in a category, say this object, and two known identity maps. Or suppose we have three objects in a category with the maps. Suppose this is the map F, this is the map G, then by definition this is the map G composed F. Or suppose we have a category with five objects, say 1, 2, 3, and 4. And suppose we have one object here. So suppose this is the map, say, um, suppose this is the map F here, this is the map G here, this is the map, say, H here, and let us call this map, say, J. Sorry, this is J here. This is the map J. Then by definition, this is the map J composed F, which is same as H composed G. So this map is J composed F, which is same as H composed G. And suppose this is the map, say map, let us call this map K. Then this map is K composed J. So these are some more examples of categories. Now there are categories which contain no maps at all apart from the identities. So this is the second example. So there are categories with which contain no maps at all. So by no maps would not mean the identity maps, because identity maps they have to be there by definition. So this is apart from the identities. So these are called discrete categories. These are called discrete categories. So in discrete categories, each object is totally isolated from its companions. So in discrete categories, each object is, totally isolated. So from its companions. So such categories can be drawn like points, isolated points. So these points they just have the identity maps on them, and we do not have any non-identity map there. Now let us do one more example. So since we know um, there is a there is this category GRP, category of all groups, but we can view a group as a category that has only one object and in which all the maps are isomorphisms. So a group can be viewed as, so we can identify a group as, so this can be viewed as a category with uh, just one object, say, with one object and in which all the maps are isomorphisms. Isomorphism from the group to itself. So consider to illustrate this, let us consider a category. So consider a category, say fancy A, with just one object, say A. So then this category A consists of a set of maps. Then the category A consists the set home AA. The set of all maps from A to A. And so first of all, it contains this set home A to A. Also, it contains an associative composition function, composition function, say O. So this composition function O, this is a function from home A to A times home AA to home AA. And so it consists of the set home AA, the associative function, I mean the composition function O, and a two-sided unit, and a two-sided unit, I mean a function 1 sub A from, I mean this belongs to home AA. Since every map in A is an isomorphism, then every element of home AA has an inverse with respect to this O. So since every map in the category A is an isomorphism, then every element of this set home AA has an inverse with respect to this composition function with respect to O. And this makes home AA into a group. So this makes home, I mean this set home AA has everything that is needed I mean that is needed to be a group. So this makes this set into a group. Let us call this group G. So let us note this group by G. So G is the group home AA. Then the situation is like this. I mean, then we have the following situation. So we have the category A with single object. So we have category A with single object, and here we have a corresponding group G. Here we have maps in A, and those maps correspond to the elements in G. We have the composition in A, and here we have the binary operation, say dot in G. Here we have the identity uh, isomorphism on A, and that corresponds to the unity, I mean the identity element of group G. Let us note this by 1. So that means we can identify a category with one object with a group. Now, before we do another example, let us define what a pre-ordered set is. So we have a definition. So a pre-order is actually a binary relation, which is reflexive and transitive. So pre-order is a binary relation. which is a reflexive as well as transitive. So a pre-ordered set. So a pre-ordered set, say S with less or equal sign, is a set S together with a pre-order less or equal on it. For example, uh, let us do examples. So if we consider the set R of real numbers with the pre-order less or equal to where less or equal has its usual meaning. So this less or equal has its usual meaning. So then this is a pre-ordered set. So this is a pre-ordered set. Let us do one more example. So let us consider set A. Suppose it has elements, I mean, of the form, 1, 2, up to 10. So it has first 10 positive integers. And let us consider S to be the power set of A. Set of all subsets of A. So this is actually the power set of A. So then this S less or equal is a pre-order, is a pre-ordered set where this less or equal to is inclusion. So where less or equal to is, this is the containment, the inclusion. Then one can see that this relation is reflexive as well as transitive. If I take the set, uh, say integers with less or equal pre-order, where a is less or equal to b if and only if a divides b. So where a is less or equal to b if and only if a divides b for all integers a and b. Then this order is also a pre-order. So this is a pre-ordered set. Now let us do the other example, example 4. So a pre-ordered set can also be viewed as a category. So we can identify a pre-ordered set with a category in which for each for each object is A and B, there is at most one map from A to B. So pre-ordered set. So we can view this as a category, say fancy A, in which for each, say, element is A and B, objects A and B in A, there is at most one map from A to B. So there is at most one map from A to B. Now to see this, consider a category. So consider a category, say A, with this property. I mean, between any two objects, there is at most one map. So with this property, now let us write. So let us write A is less or equal to B. Uh, I mean, let us write. I mean, A is less or equal to B if there exists, say, a map from A to B for all objects A and B in the category. Now, since A is a category and categories have composition, so if A is since this fancy A is a category and categories uh, have composition, so therefore, if A is, I mean, object A is less or equal to B is less or equal to C, then A is less or equal to C. This follows from the composition in the category. So this is true for all A, B, C in the category. Now, since categories also have identities, so since categories also have identities, we have A is less or equal to A for all objects A in A. So since I mean the associativity and the identity actions are automatic, so they follow easily. So the associativity and identity action, so they are identity actions are automatic, so they follow easily. So A amounts to a collection of objects equipped with a binary relation, say less or equal to, that is reflexive and transitive. So that is this fancy A together with this less or equal to is a pre-order. So this fancy A amounts to a collection of objects equipped with binary relation, equipped with a binary relation less or equal to. And this binary relation is, so we saw here, this is transitive and this is reflexive. That is reflexive as well as transitive. So that is, if we look at the set A equipped with this order, so this is a pre-order. So one should keep in mind that we call a pre-order a partial order if we have two elements, say A and B, such that A is less or equal to B and B is less or equal to A, then A has to be equal to B. So in that case, we call the pre-order to be the partial order or OSET. So we have this definition. So an order is a set, I mean, an order on a set is a pre-order, say less or equal with the property that if, say, we have object A which is less or equal to B, and B is less or equal to A, then A is equal to B. So this is true for all A and B. So these ordered sets are called partially ordered sets or posets. So they are called partially ordered sets or posets. Now we are going to discuss the ways of constructing new categories from old one. So the first construction involves the principle of duality. This is the construction one. So so we are so what we are going to do, so we are, suppose we are given a category A, then with the help of this category we can form another category. So the first construction involves the principle of duality. So every category, say fancy A, has an opposite or dual category. So opposite or dual category. And so we denote this opposite category by A together with the symbol OP, which stands for opposite. So this is defined by reversing the arrows. So formally, the object is in, I mean, the opposite category. So they are same as the objects in the given category. And if I look at the morphisms, so if I look at the morphisms in the opposite category from object A to B, so they are actually the morphisms in the given category from object to B to A. So that means the arrows and they get reversed for all objects, for all objects A and B. The identities in the opposite category remain as they are. I mean, they don't change. The identities in the opposite categories are same as in the given category, but composition gets changed. I mean, composition in the opposite category is same as in A, but with reversed arguments. But with reversed arguments. That is, if we are given maps So suppose we are given maps, say f and g from object A to B and B to C. So this is the map F and this is the map G. So they are the maps in, suppose they are the maps in opposite category. And then what happens in the original category? So these maps goes like this. So F is a map from B to A and this uh, G is a map from C to B. So they are the corresponding maps in the given category. So that means then the composite map, which is a map from A to C, is the map GF. So this is in the dual category, opposite category. So this corresponds to the map. This corresponds to the map, a map from C to A. So this direction changes. So this is the map F composite G. So this is in the given category. So in short, so in short, if the given category is like this, so it has the class, I mean the class of objects, the class of morphisms, the identity map, and the composition. Then the what happens in opposite category is that the objects remain same. The morphisms, their direction gets changed. The identity map remains same. I mean the identities remain same, and this composition this also changes. So this is what we mean by the opposite category. So for example, so if suppose we have a pre-ordered set, so suppose this is a pre-ordered set, then we know we can identify this with and this set with a uh, category. So consider as a category. So if it's a pre-ordered set, then uh, considered as a category A. So if we view this as a category A, then the opposite category is the set X with reversed order. So we have one final remark here. So why do we need this dual category? I mean this dual concept. I mean the principle of duality. So the principle of duality, this is fundamental to the category theory. Informally, it states that every categorical definition, theorem, or proof has a dual obtained by reversing all arrows. So the principle of duality. So this is fundamental to category theory. So informally, it states that uh, every categorical definition or theorem and proof has a dual obtained by reversing all the errors. So this is obtained by reversing all the errors.